Okay, go ahead and start. If you still have your exam out, you can just pass it in, and I'll deal with uploading it myself. Okay, I have a demo that I want to do, and I'm waiting on a technician to bring some equipment that is a little tricky to get. So unfortunately, it's not ready to go, but hopefully before the end of class, Carlos will show up with the liquid nitrogen that I need, and then we can have some fun with it. So I'm going to skip ahead a little bit. Today we're going to move on to chapter 14, which is where we really take this idea of magnetism that we've been dealing with for the last few weeks, and we bring it into circuits. So we look at circuit elements that take advantage of some of the magnetic effects that we've discussed. Hey, Carlos, come on in. Perfect timing. Over here is fine. All right. Okay, all set. Do I need to return this to you afterwards?
Yeah. Yeah, I mean, yeah, you can swing by. Or like down here.
Okay. Thank you. All right, so I wanted to demonstrate a really cool effect that relies on superconductivity. So I have a superconductor here, which is a material that has zero resistance. Or at least it has zero resistance when it's a superconductor. This particular superconductor requires it to be cooled to liquid nitrogen temperatures, which is why we have the liquid nitrogen here. So is that live? Yeah, there we go. Okay, so I'm going to cool this. So liquid nitrogen is at about 77 degrees Kelvin. So that's roughly 200 degrees below 0 Celsius. So this is a demo that's related to induction. We know that when we take a material, a conductor, and we take that conductor and we place it in a changing magnetic field, a current gets induced in the conductor that prevents the field from changing. So we know from the right-hand rule in Lenz's law that if we take a conductor or a ring of conductor and we bring it near a magnet, so I have a magnet, let me bring it out. I bring it near a magnet, it's going to induce a current in the conductor so that the current that's induced produces a magnetic field that opposes any change in magnetic field. So if I take my conductor over here, let's say this was a conductor, over here there's basically zero field, and I bring it near the magnet, now there's flux going through it. So it's going to try to oppose that change and induce a current that opposes that. And that's going to reduce the amount of field in here temporarily. But eventually those circulating electrons are going to lose energy due to heating up the material through the resistance. And so that current slows down and the flux then seeps through our material. What do you think would happen if there were no resistance? My material that had zero flux through it, I bring it near the magnet. A current's induced that opposes the change, so it tries to keep the flux zero. And unlike a regular conductor, where eventually that current will die off, that current will just keep going and maintain that zero flux condition. So that results in some interesting behavior. And let me see if this is tricky to work with. I mean, the mask and my goggles are fogging up, so not a good combination. pour some of this out. You get some nice Halloween fog effects. Bonus. Pour a little on the table. All right, that worked. I forgot that my tongs are metal, which is not a good. I had some plastic tongs here. They broke. I guess I can make it work. That's underwhelming. All right, let's try it. Let's try it over here. All right, it's not cold enough. That's ridiculous. Let's let it go a little longer. As long as we hear the bubbling, it's boiling the liquid nitrogen. And if it's boiling the liquid nitrogen, it's warming up the liquid nitrogen and it's still cooling off. So we need it to stop bubbling. Seems to be doing. You can see the frost on the tongs. Cold pretty quickly. I'll give it just another minute. So this is just a magnet. It's a rare earth magnet. It's very strong. Up here, there's a whole circular array of magnets. There's actually two sets of magnets with opposite orientation. So the inner ring has, let's say, the North Pole facing up, where the outer ring would have the South Pole facing up. So what that does is it acts like a horseshoe magnet, basically causing fields to go from the North Pole to the South Pole, but in a way that's symmetric, cylindrically symmetric. So it forms like a little track. Still bubbling a little bit. So this particular superconductor is what's called a type 2 superconductor. And that means, if I go into my explanation, I was going to do this after the demo, but since it's taking a while to cool off, I will do this now. This is what the magnetic field might normally look like when I place a conductor or a material above the magnet. It really has no effect on the magnetic field, so I see these field lines going from the North to the South Pole. If it's a superconductor, it will have the effect of not letting any magnetic field through. This is called the Meissner effect, and it's basically the idea of what I said before, which is you start with no flux through it, and you bring it to a magnetic field, there still is no flux. So it's basically producing little eddy currents inside that oppose that flux, and so the field lines have to bend around to the superconductor like that. And that will actually give rise to levitation. So we're going to be able to levitate this over our magnet. But this is a type 2 superconductor, which means it has these little impurities in it. So these little gray dots are meant to represent impurities. I lost my pointer, so I can't highlight that, but those gray dots represent impurities, and they're regions where the field can go through the superconductor, because they're not superconductive. So the field lines will squeeze together and channel through this little thin superconductor where there are impurities. And one of the things that we're going to learn today is that magnetic fields store energy. And so when you squeeze together the field lines like that, there's energy stored in that. And so if we were to try to move the superconductor, those field lines have to follow the impurities. And so if we move it just a little bit, the field will move around to follow those impurities. That's called quantum locking, or pinning of the field through the impurities in the superconductor. And what that's going to do is it's going to require work to extend the field lines from their original position when the object is moved. And what that means is it's going to take energy to move this. So it's going to be in a stable equilibrium, sitting above our magnetic field. And that's what we want to see. So let's give it a go. I'm going to transfer most of the liquid nitrogen out of here. This time I'm not going to pour it out onto the table, because I think that probably helped warm it up. Yeah. You want to see what I'm doing? All right. Thank you. There we go. I can't see a thing because of all the fog here. I can't blow it out with the mask on. I said I wasn't going to pour it, but here I am pouring it. Metal. Metal. There we go. And so you can see that it's suspended, and because of the cylindrical symmetry of the magnetic field, it can actually move along that cylinder without any change in the energy, because the field is symmetric. And it's levitating. I don't know if you can quite see underneath that. I can adjust the orientation a little bit and give it a little kick. All right, so there's a lot of work for short payoff, but kind of fun. I will throw this back in, and then maybe if we have a chance later, we can play with that a little bit more. There's a few more things I wanted to do, but it's hard to do with metal tongs and foggy glasses and all that, so we'll move on. Okay, so with that, we're going to move into how these magnetic effects can be implemented in circuit elements. So we're going to introduce something called mutual inductance, which is closely related to concepts that we've already been discussing. And then we're going to take that and use it to describe self-inductance, which is a related concept that gets used in circuit elements. So to start with, let's consider the case where we have got two. Give me 1 second here, because I seem to not have my pointer. I'm not sure why. All right, we'll have to troubleshoot that later. Okay, so we've got two loops. One loop here, we can have as many turns as we want, and another independent loop here from a different circuit. And the question is, if we send a current through this first loop, I1, will there be a current induced in circuit 2? Or more specifically, will there be an EMF induced in circuit 2 that will then drive a current? And we know the answer is yes. If that field produced by current 1 is changing, that means the flux through circuit 2 is also going to be changing. And if it's changing, then Faraday's law tells us there will be an induced EMF. So the EMF in circuit 2 is minus the number of turns in that coil times the change in flux of circuit 2. Okay, so what we want to do is relate the EMF induced here to the current over here. Okay, so we're going to write that the flux in loop 2, so phi is the flux through a single coil, and N2 is the number of coils. That's like the total amount of flux that's relevant up here in Faraday's law. We're going to say that's proportional to the current, which it is because the magnetic field produced is proportional to the current. And then that magnetic field is the flux is proportional to the magnetic field. All those constants of proportionality, we're going to group them together into this quantity N that we call the mutual inductance. Okay, so when we put a current through coil 1, we'll get an EMF in coil 2. And if we substitute in our expression for the mutual inductance, it's N phi over I. We can also show that we can describe the flux or the mutual inductance from 2 to 1 the same as it is from 1 to 2. So if we define current in 1 producing a flux through loop 2, we get the same mutual inductance as we get for finding the current in 2 producing a flux through 1. So there's symmetry there. And with this definition, we can write that the EMF induced in coil 2 due to a change in current 1 is minus M di dt. Right? When we plug in our value for M, we're getting the change in flux with respect to time, which is just Faraday's law. So this is just basically rewriting Faraday's law, where all the constants that relate how current here relates to flux there are grouped together in this quantity M, the mutual inductance. So that quantity has units of Henry, which is 1 Weber, which is a unit of flux. So 1 unit of flux per amp of current. So we can see it's a flux per current. And typical values for sort of laboratory scale configurations are going to be millihenries or microhenries. So most sort of realistic circuits that use this mutual inductance are going to have relatively small values for their mutual inductance. So let's see an example of how this works. Let's consider 2 solenoids. This black one here has N1 total turns and has a length of little l. And then this blue one wraps around it and has N2 total turns. And we want to find the mutual inductance between these 2 circuits. So we have to work through how much magnetic field is produced by a current in coil 1, in solenoid 1, figure out how much flux that produces through coil 2, and then once we know that, then we can find the mutual inductance from that total flux through coil 2 divided by the current in coil 1 that produced it. Okay, so we know how to find the magnetic field from a solenoid. In the core of a solenoid, the magnetic field is going to be basically translationally symmetric and passing through, and the field outside the solenoid is negligible. Those field lines will loop around, but they're so spread out and they're outside the core that they're negligible. Inside the core, they're concentrated. And that means whatever field goes through this inner solenoid is the exact same field that goes through this outer solenoid. So that coupling is straightforward. The main goal here then is to calculate the magnetic field in the core of a solenoid. And you can certainly look this up because it's something that we've done before, and there's an expression in the book that gives the result, but I'll remind you that it comes from Ampere's law. And so if we do a cutaway of a solenoid, this is worth remembering how to do, we have current, let's say, pointing in on the top set of cross sections and coming out the bottom. Current's doing this. And then we draw a little Amperian rectangle that we're going to integrate the magnetic field around. And we said inside the core, the magnetic field is basically translationally symmetric, and that means it's constant along this path from A to B. It's perpendicular to the path from B to C and from A to D, so the dot product here is 0 over those 2 paths. And if we go far enough away, then it's negligible on the path from C to D. So when we apply Ampere's law, the left side, where we integrate v dot dl, comes entirely from going from A to B along the magnetic field, which is constant. So it's just whatever that magnetic field is in the core times that length from A to B, which I'll call L. So that equals mu naught I times mu naught times the enclosed current. So the enclosed current is going to be whatever current is passing through this wire times the number of wires we have enclosed in that length L. So if little n is the number of turns per unit length, and we multiply that by L, that gives us the total number of turns. And now our L's cancel, and we get V is mu naught I n. And that's the magnetic field inside the core of a solenoid. Now that we have that, the flux is just that magnetic field times the area. And I plugged in N1 divided by L for my particular solenoid here, because I had N1 total turns over a length L. So the little n was the number of turns per unit length, and now I've got a number of turns and a length. But all that flux that goes through the black solenoid here also goes through the blue one, since the blue one surrounds it. So the flux through circuit 2 is the same as the flux through circuit 1. And so I can write the mutual induction as N times the flux through circuit 2 divided by the current in circuit 1. That's our definition of mutual induction. So I keep my N2. My flux I get from right here, mu naught N1 A over L. And when I divide by the current, it cancels out that I1. And I get a mutual induction here that depends on the area of the solenoid, the number of turns of each of the two solenoids, and the length of this one that's generating the field. So the mutual induction shouldn't depend on the current, right? Because it factored out the current. It was all the geometric factors that related how much overlap there was in the flux of the two circuits. And it should be symmetric between coils 1 and 2. Because we said whatever mutual induction is from coil 1 to coil 2 is the same as from coil 2 to coil 1. So if we swap the 1s and 2s, we should get the same result. And we do. Bella? A is the area of this black solenoid. So it's like the size of this circle here. That's the A. And it came from the flux that we had generated in the solenoid. And the little L is the length of that solenoid that's generating the current. And that comes into play because our magnetic field depends on the number of turns per unit length. So there's the number of turns, there's the length. Okay, so we can use this, for example, to find the EMF in the blue coil when we put a current through the black coil. And so if the current through the black coil is sinusoidal, like this, I naught cosine omega t, that might be something like you'd have coming out of a wall outlet, right, where the frequency is 60 hertz, and so the current is oscillating. We can say the EMF is minus m di dt. That's our definition for the induced EMF due to mutual induction. So calculating di dt is just a matter of taking the derivative of cosine. So we get a minus sign, and then that omega pops out front when you do the chain rule. And now plugging that in here, and plugging in our value of mutual induction that we got on the last page, we get an expression for the EMF in coil 2. And if we plugged in some numbers, sort of tabletop scale numbers, so a half a meter length for our solenoids, a 10 centimeter square area, 1,000 turns and such, we're only getting like 47 millivolts coming through for like 5 amps of current. So you can see that the induction is small. We're not getting a huge amount of voltage at the output. But there's something. You could use this to charge a toothbrush. And if you have an electric toothbrush, you do. Right? You could use this to charge a cell phone if you had a wireless phone charger. And that's the principle by which those wireless chargers are based. So just as one coil can induce an EMF in another coil, we could ask, well, doesn't this changing flux produced by this current, doesn't that produce an EMF in the coil itself? And the answer is yes. So if I have a current flowing through here, there's a magnetic field produced in this loop. And if that current changes, then the magnetic field will change. That changes the flux through the loop. If the flux changes, there's an EMF that opposes that. That means when the current through a loop changes, there's an EMF induced. And so we can say that EMF is going to be proportional to the rate of change of current. And this is an expression that looks exactly like the EMF induced in coil 2, with the change in current in coil 1, only now it's the EMF induced in the same coil that the current is in. So we call this constant here L, the self-inductance. Has the same units of Henry as the mutual inductance. And this is useful as a circuit element, because you can make a circuit element that has a bunch of coils of wire with the property that when you try to put current through it, it resists that. It produces a voltage that opposes that change in current. And there's reasons that's useful. If you want to have a constant current flowing through your circuit, but you have various noise sources that are causing fluctuations, you can add an inductor that will oppose those fluctuations, use it as a noise filter. And so this self-inductance is a property that's widely used in circuit elements, and because it's widely used, we simplify it, just call it inductance. You can say, what is the inductance of this coil? Or what is the inductance of this inductor? So the circuit element that uses this effect is called an inductor. Here's a picture of a bunch of inductors. They look like coils wrapped around little chunks of iron, because that's exactly what they are. And they're typically toroids, because that contains all the magnetic field in that core, so you don't have stray magnetic fields that could interfere with other circuits in our system. So these toroids can have a large self-inductance, but very low mutual inductance, because their magnetic field doesn't extend out to where there'd be other circuits. So these are actual inductors. If you ever open up any power electronics, anything that plugs into the wall, you will probably see an inductor in there that's used for various power filtering functions. And this is what the schematic diagram of an inductor looks like. It's a little bit like a resistor. Remember, a resistor is like a jagged line that is meant to represent a bunch of wire crammed into a little package. This is similar, but it's more circular, so it's meant to represent a coil of wire crammed into a small package. So let's see if we can calculate the self-inductance of a toroid, since so many of these inductors are toroidal in shape. So we'll assume that there's n turns of wire on this toroid. And we're going to use the results that we got from the solenoid rather than rederiving this. We're going to use the magnetic field from the solenoid, which was mu I n in the core. And a toroid is just a long solenoid that we wrap into a circle. Okay, so n was the number of turns per unit length. So we're going to say that's n, the total number of turns, divided by the length of a circle is 2 pi r, right? The circumference of the circle. That's essentially the length of our solenoid that got wrapped into a circle. So we just sort of reuse that result for the magnetic field and then say that the flux through that core is the magnetic field times the area. So our mu I times n over 2 pi r is the magnetic field, and A is the cross-sectional area. Right up there, it's shown. The cross-sectional area of this core. And we're calling that the self-inductance is the ratio of phi to I times the number of turns in the coil. We get this expression multiplied by n and divided by I. So there's our value for the self-inductance. Notice it has mu in it. Mu is the permittivity of, typically we've dealt with mu naught as the permittivity of free space. It's that 4 pi times 10 to the minus 7 value. But in a material, a magnetic material, mu can be larger. Just like epsilon naught was in free space, but in a dielectric it was higher. Likewise, in iron, mu is much greater than mu naught. And that tells you why there's an iron core, is it increases the self-inductance of the device. So these devices oppose changes in current through them. And we'll quantify that in a moment. But one way of understanding that is when you put current through them, a magnetic field builds up, and it takes energy to build up that field. So let's talk a little bit about the energy. The power delivered by some current, I, flowing across the inductor, produced by a voltage V in our circuit, is just going to be I times V. And the voltage across the inductor, we know, has a magnitude of L times di dt. That's sort of the definition of induction, is a changing current produces an EMF. That EMF is the inductance times di dt. At least that's the magnitude of it. So this becomes an expression for the power that it takes to send a current into an inductor. Notice it doesn't take any power if there's no current. It doesn't take any power if the current's not changing. It has to be a current, and that current has to be changing in order for it to require power to pump current through the inductor. Okay, so to figure out how much power or how much energy is stored in the inductor when it initially starts with no current through it and ends up with a current I after some time t, we'll say that energy is the power being delivered times the time over which it's delivered, right? Power is energy per unit time. So multiplying it by a time, this gives us a total energy. And we're counting how much energy we put into the inductor from our starting time 0 until time t, when the current is I, capital I. Okay, so I can write the power as IL di divided by dt, and then when I multiply that by dt, the dt in the denominator goes away. So if I'm going to integrate over I, I'm going to go from 0 to capital I. That's the change in current in the time from 0 to capital T. And so integrating this, L is a constant. I gets integrated to I squared over 2. And I evaluate it at my limits. Capital I squared, I have 1/2 L capital I squared. At 0, I have 0. So the total energy stored in the magnetic field of the inductor is 1/2 Li squared. And I asked what happens to that energy, but I already said it gets stored in the magnetic field. It takes energy to build up the magnetic field. Okay, so magnetic fields have energy associated with them. And we can consider how much energy, or the energy density, by looking at our example of the toroid, where we calculated the self-inductance a couple of slides ago. We can use that self-inductance in this expression for the potential energy, 1/2 Li squared. When we plug that in for L, we get let's say this is the total energy. If I want to calculate the energy density, the energy per unit volume, I'm going to divide by the volume of this core. And the volume of that core is, we can think about it if we unwrap it, it's like a box that has a cross-sectional area A, right here, and it has a length of 2 pi r. So if I divide the energy by the volume, I'm going to divide out the A, and I'm going to divide by a factor of 2 pi r. So I go from 2 pi r in the denominator to 2 pi r squared in the denominator. And now that's the energy per unit volume. And the magnetic field was mu n I over 2 pi r. And I've got a mu n squared I squared over 2 pi r squared. So if I just multiply this by a mu and divide by a mu, then I've got this being the magnetic field squared. And I can write the energy density as b squared over 2 mu. So that's the energy density associated with the magnetic field in a solenoid, or a toroid. But it turns out, although we did this derivation for a toroid, you could do this for any shape, you get the same result. Magnetic fields take energy to produce. And the energy density stored in the magnetic field is b squared over 2 mu. That should look kind of familiar. When we looked at capacitors, we had an energy density for the electric field that was like E squared over 2 epsilon. So we're just kind of replacing the magnetic parameters, E with B and epsilon with mu. And this is going to be important when we start talking about electromagnetic waves in chapter 16. Okay, it's the energy associated with the wave gets stored in the electric and magnetic fields of that wave. But for right now, the reason we care about this is because when energy gets stored in the magnetic field that's produced by an inductor, we can just treat it as if it's stored by the inductor. The inductor is an energy storage device, and we can talk about what effect it has on the circuit. So we know that a general way to analyze circuits is using Kirchhoff's rules. And we can do this if we know the voltage across an element. For a resistor, the voltage across it is IR. For a capacitor, it's Q over C. And for an inductor, the voltage across an inductor is L di dt. And to be specific, when we go through a circuit, the rule is if we're going in the direction of current, then we get a voltage drop of L di dt. Okay, so just like when we go through a circuit in the direction of current, and we cross a resistor in the direction of current, the voltage drops by an amount IR. If we go across an inductor in the direction of current, the voltage drops by an amount L di dt. Okay, and if we go against the current, then the voltage goes up by that amount. So actual inductors are made up of long wire wrapped in a coil, and resistors are made up of long wire scrunched up into a little element. And so it's probably not surprising that anything that serves as an inductor is also going to have some resistance, because the wire in the coil has resistance. So real inductors are typically modeled as an ideal inductor in series with some resistance, the internal resistance of the inductor. And so it's really important to understand how not just an inductor behaves in a circuit, but how does it behave when it's in series with the resistor? Because every real inductor you work with is going to behave like an ideal inductor in series with a resistor. So circuit with a resistor and inductor in series is called an RL circuit. Okay, so let's consider a fairly simple RL circuit. Here's our R, and there's our L, and we have a voltage source with a voltage of E, strict E, EMF. So it's like a battery up in the top. And because inductors are really only interesting when current is changing, I need to be able to change the current through the circuit. So I put in a couple switches, switch 1 and switch 2. So initially, let's say both switches are open, there's no current flowing, and then at time 0, I close switch 1. So basically, I just connect the battery across this RL circuit. So I'm going to expect some current to flow. It's going to flow from the positive terminal of the battery around the circuit to the negative terminal. So that's counterclockwise. Meaning on the bottom here, current's going to flow from A to B to C, left to right. And I want to figure out how much current flows as a function of time. Okay, so to do that, I'm going to use Kirchhoff's junction rule around the outer loop. I know the voltage drop from A to B is given by Ohm's law. It's IR. And the voltage drop from B to C, because I'm going in the direction of current, is L di dt. So when I apply Kirchhoff's loop rule starting here, I go up in voltage by an amount E, and then I go down by IR, and then I go down by L di dt, and I'm back to where I started. So the total voltage change has to be 0 around that loop. So now I'm going to take that expression and I'm going to take all the terms that have an I in them and put them on the left, and all the terms with a T and put them on the right. Okay, so I can rearrange it to write it like this. And the reason I do that then is I can integrate both sides. And on the left, I'm going to get a function of the current, and on the right, I'm going to get a function of the time. I'm going to try to solve for the current as a function of time. So let me integrate both sides. On the right, this is trivial. Right? R over L is a constant. That comes outside the integral. I'm just integrating dt. So that's going to give me t. And my limits are from 0 to some time. On the left side, the easiest way to integrate this is to recognize that the denominator, if I substitute in like u for this quantity in the denominator, then du becomes the numerator, and it's going to integrate to give me natural log. So I'll do that and evaluate at the limits. Natural log, when I plug in I for this parameter in the denominators, I minus e over r. When I plug in 0, is just minus e over r. And because I'm subtracting the first limit from, or the second limit from the first, for natural logs, it's like taking the ratio in the argument. So I get this on the left side. And on the right side, it says integrating this is trivial. It's just multiplying RL by T. So I've done that there. And now my goal is to solve for I of T. So the first step is to take E and raise it to the left side and raise it to the right side. So when we raise E to the natural log of something, we just get that something. And then on the right, we have E to the minus R over LT. And now, at this point, it's just simple algebra. I can multiply both sides by E over R, or minus E over R. And then I can add that E over R to both sides and factor out the common term on the right, and get an expression for the current as a function of time. So let me look at this expression. Remember, I just closed the switch. There was no current flowing through the inductor. So at time 0, I expect there not to be any current through the inductor. So when I set t equal to 0, this goes to 1. And I have 1 minus 1, which is 0. So initially, there's no current through the inductor. But then, as the time increases, this exponential term gets closer and closer to 0. And as it gets closer and closer to 0, this term in parentheses gets closer and closer to 1. Which means the current gets closer and closer to E over R. And so it has this asymptotic approach to E over R. Now, if the inductor weren't there, if it were just a wire between B and C, I would expect that the moment I close the switch, the current would be E over R. I would expect that this would just be a step up to E over R and would be a flat line. But I don't see that. What I see is it takes time for the current to grow, because the inductor is resisting a change in the current. And it started out at 0, so it tries to keep it at 0, but it asymptotically approaches this final value. So we have the same sort of way to characterize the rate at which it reaches this final value that we did for charging and discharging capacitors. We can't ask how long does it take to reach the final value, because it's asymptotically approaching it. We'll never get there. But we can talk about how fast does it take to get to the point where this term here is e to the minus 1. So basically, when t equals L over R, then this term here will be e to the minus 1. And that's sort of our characteristic way to measure the time it takes an exponential growth or decay to occur. So that time constant is L over R. The bigger the inductor, the longer that time constant. If the inductor weren't there, if it were just a wire, the inductor would be 0, and your time constant would be 0. You would instantly go up to that max value. And we can take our circuit now and we can open switch 1 and close switch 2 and ask what would happen. So we've taken the battery out of the circuit. So you might just expect if there's no battery supplying an EMF, there would be no current. But because there was current flowing through our inductor and it resists any change, the current doesn't instantaneously stop. And so we can apply Kirchhoff's rule around this lower loop. It looks just like before, except there's no longer an EMF current. So we just have a voltage drop of IR plus a voltage drop of LVIT equals 0. And so again, we'll put all the terms with an I on the left and all the terms with T on the right, and integrate both sides from our initial current to some final current as we go from time 0 to time t. So it's the same steps that we did before. Integrating this just gives me natural log, and I evaluated the limits, which is I of t and I naught. Integrating this gives me R over L times t. And then I take E and raise it to the left side to get rid of the natural log. On the right side, I end up with e to the minus R over L of t. And so multiplying by I naught gives me the current at some time is exponentially decaying. At time 0, where this factor is 1, the current starts out at I naught. It starts out at the same value that it had before I closed the switch. But then it exponentially decays to 0 because there's no longer a battery supplying an EMF to my circuit. And again, we can talk about how long it takes to decay to within 1 over E of its final value, and that time is again L over R. So we call L over R the time constant for the circuit. And while it's useful to be able to describe the time dependence using these exponential decay equations, it's also really helpful just to understand conceptually sort of the limiting behaviors. Limiting means what happens at the lower limit at time 0, and what happens at the limit of t goes to infinity. So what's the very first thing that happens, and what's sort of, where does it end up? Okay, so immediately after we close the switch or do something to change the current in the circuit, the inductor makes sure that nothing changes in the inductor. The current through the inductor stays the same. But eventually, it allows the current to flow through, and because it's literally a coil of wire, it ends up behaving just like a wire with no voltage across it. So those are the two limits. And so I want to give you a chance to try to analyze a circuit here. There's 7 questions asking what happens when I take this switch and first I close the switch, and then question 1, what happens to the current through R1, through R2, and what is the voltage across the inductor? And let's come back to this. We've got 5 minutes, you're not going to finish this, and we've got a tank of liquid nitrogen. So let's prioritize here. All right, what can we do? We can freeze candy bars. So I've got candy bars. Let's freeze the baby Ruth. And while that's freezing, I will pull out our superconductor. We can have some fun with it. All right, let's see if I can levitate this. That's true. Now let's put it on the track. Maybe that'll work a little bit better. It's warming up quickly because there's not enough liquid nitrogen in the submersive, so it's. All right, well that's pretty disappointing. Let's see if the baby reef is any better. Okay, so what we should be able to do is, it's so brittle now that we can shatter it. And while normally you get a smushed baby reef, in this case, we just got little pieces. So that's kind of fun. I wasn't really prepared. With proper preparation, we could drive in a nail or something with that, but we'll stop there, and we'll return to that activity on Thursday. So have a good week. Come, please take some Halloween candy with you on your way out.